Warning, the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is not a review for a pre-calculus student. I say that as a surprise because most videos in the trigonometry review sections are all review, or mostly review. But this is something that we personally, or not personally, but at our college, we do not teach areas of triangles in our trigonometry course. We save that for our pre-calculus. I don't know why, honestly. But here we go. So I'm going to actually teach this. Theorem, area of a triangle. So you have a triangle. By the way, this triangle is not necessarily a right triangle. It could be an obtuse triangle or an acute triangle. It could be equilateral, doesn't really matter. Or it could be a right triangle. But the area of a triangle with side lengths A and B and with included angle between those those sides being theta, that area is 1/2 AB sine of theta. This area formula is actually more important than most people think. It does come up quite a bit in mathematics, so it's good to really get nailed down this theorem. Now, rather than proving it for a right triangle, which would be silly because that's way too specific, I'm going to prove it for an obtuse triangle, but this proof works. That's actually the harder proof. This proof actually works for all triangles. Okay, so the arguments are going to be the same no matter what. So let's see, we want to showcase the area of this triangle is 1/2 AB sine of that included angle theta right there. Well, we know that, let me write this down. We know that the area of a triangle is 1/2 its base times its height. Looking at this picture right here, the base is really not long enough for me to talk about its height. So what I'm going to do is extend this out a little bit. And we're going to put in, let me do an imaginary height here, and then we'll talk about its base. Okay, so we've done that. Notice that we've created a right angle here. That's going to be critical for us. And this is the height. Now, when I say the height, I really mean the height of this triangle. We're really concerned about finding this highlighted area here. Not the area of the red triangle, but the area of the yellow highlighted triangle. So let's see, we need the height of that and the base of that yellow highlighted triangle. Well, the base actually is A. So I'm going to write that down. This is thus the area is 1/2. The base is of length A and the height is H. And now I can take a look at the big triangle. The big triangle being, I will draw this in, actually I'll use this pen right here. I think it's better. This big right triangle right here, that is definitely a right triangle. And I would love a way to relate this angle theta to this height to this side B, because I'm trying to prove that the area is 1/2 A, which I have so far, times B sine of theta. So I'd like to get B into this. And if you think about that, that angle theta is related to H and B via the sine function. The sine of theta is equal to opposite over hypotenuse. That's just from our right triangle trig. So therefore, H must equal B times the sine of theta. So this is equal to 1/2 A times B sine of theta. And that's it. That's the proof. QED, we're done. There's no other thing there that we need to do. We've proven that the area is 1/2 AB sine of theta. Now we just need to actually use this theorem. It's a really nice theorem to use, actually. Let's go ahead and use that information to go and find the area of the shaded region. And I do have to kind of give you a length here. So let's say this is of length 10. 10 inches, 10 meters, 10 feet. I don't really care. It's not that big of a deal. But find the area of that shaded region. How are we going to do that? Well, often in mathematics, finding one object, the value of this, is actually harder than finding the area of the unshaded region. So if we can find the area of the unshaded region and subtract that from the full area of the circle, we will have the area of the shaded region. So the area of the full circle, well, that's kind of easy, right? Area of circle, we know, is pi r squared, which is 100 pi. So we know the full area that we're working with is 100 pi square units. And now we're going to go ahead and start kind of subtracting things off here. And I'll start from the bottom up. Let's subtract off the area of this part, this area of a sector here. We're going to subtract off all of that. And as I recall, that's a video that I've done earlier. The area of a sector is 1/2 r squared theta. So we're going to go ahead and subtract off 1/2 r squared theta off of this. And remember, theta for that formula has to be in radians. So let me go ahead and write that formula down. I'm just having too much fun shading, honestly. But here we go. All right, so the area of blue is 1/2 r squared times the angle, again in radians, not in degrees. Well, we do know that r squared is 10 squared, and we just need to know what is that angle in radians. Well, 150 degrees was taken by this big opening angle here. So 360 minus that is 210. So I know that this angle right here is 210 degrees. That's 180 plus 30. Let me write it that way. 180 plus 30. And so that would be pi radians plus pi over 6 radians, or in other words, 7 pi over 6. That's going to be very helpful for us. So that's what the radian measure of that angle is, 7 pi over 6. And now we can finish this out. That's 1/2 of 100, or 50, times 7 pi over 6. There's really not much I could do here. That's 7 times 25. 7 times 25 pi over 3. And then 7 sets of 25 would be for 175. 175 pi over 3. And there's nothing else you could do with that. That's locked down. All right, so full area of the circle is 100 pi. We're going to subtract off that blue area, which is 175 pi over 3. And we're also going to subtract off the area of this triangle here. And we have just learned how to find the area of a triangle. So let's go ahead and compute the actual, I'm just having too much fun again. There we go. Let's go ahead and compute the actual area of that triangle. All I really need are two sides and an angle between them. And luckily, I have two sides. The two sides are the radii. So the left-hand side is 10, right-hand side is 10. The angle between them is 150 degrees. So this is going to be 1/2 10 times 10, 1/2 10 times 10, times the angle between those two sides, which is, or the sine of the angle between those two sides, which is a sine of 150 degrees. Now people will ask, wait, aren't I supposed to do this in radians? No, when you evaluate a trig function, you could evaluate in degrees or radians. It actually does not matter. The reference angle for 150 degrees is, let me leave a little space there, is 30 degrees. And we also know 150 degrees is in quadrant 2, and the sign is positive in quadrant 2. So that space was just in case I needed a negative sign. I don't. And we also know from our special triangles, 30, 60, 90, 1, 2, root 3. The sine of 30 degrees opposite over hypotenuse is 1/2. So that's 50 times 1/2, or in other words, 25. That is the area of that red region. So we want to take the full circle, subtract off the blue region, subtract off the red region, and then we'll have the area of the yellow region. We want this area. So area, I'll write it in black now. The area of the yellow region is the area of the full circle, 100 pi, minus the area of the blue sector, 173 pi over 3, minus the area of the red triangle, 25. It does not clean up nicely, but that is the value. I suppose that you could find like denominators here. That'd be 300 pi minus 175 pi all over 3. The minus 25 is just going to have to stay out back because that doesn't clean up very nicely. So you get 125 pi over 3, 7, 8. Yeah, that does not simplify. And so that's as good as it gets. As a decimal approximation, I might as well just do it. 125 pi over 3 minus 25. I get 105.9 roughly square units. Roughly 105.9 square units. All right, so that is a good area problem. Wonderful area problem, in fact, because it involves a little bit of critical thinking, which I'm a huge fan of. Now we have this example. This example tends to be an issue for a lot of students, so that's why I decided to do it. You have a log, a cylindrical log, and you're going to cut a rectangular beam from it. What does that mean? It means that you have this log. I'm going to erase this in a moment, but you have this log and you're going to plane it. You're going to cut it, run it through a machine to get a rectangular section out of it. A beam that you can build something with. Okay, so that's what that actually means. So we're going to take a look at the front facing the cross-sectional area of this log. So there it is right there. They tell us it has a diameter of 50 centimeters. And they want us to express the cross-sectional area of the beam as a function of the angle theta. Now, what the heck do they mean by that? It's because normally in a textbook, they would hand you a picture of this. I'm just not handing it to you. I'm kind of creating it on the fly. But let's go ahead and draw in what they mean. So I've drawn in here these slices, right? It doesn't have to look like this. There's a lot of placements or a lot of different rectangles you can cut out of this. I'm just giving you an example of one. And let's call this angle right here theta. Great. So now we have everything set. And we're told the diameter of this is 50 centimeters. Express that area of the beam, this area of the beam. Let me highlight the beam area here in yellow. We want to express this area as a function of that theta right there. Remember, area of a rectangle is very simple. It's just length times height, or width times height, or length times width, or whatever you want to call it. It's all the same thing. So I'll call this length and I'll call this height. And we know the area is length times height. But the length here, remember the diameter of this is 50 centimeters. So let's see what trig function relates that angle to, and in fact, let me draw this in because we have this right triangle right here. I didn't draw the right angle in, but we have a right triangle right here. And I'll just put the right angle in there. So what trig function relates theta to length and that 50? That'd be the cosine. The cosine of theta is adjacent over hypotenuse. And the sine of theta actually is opposite, again, over hypotenuse. And so you find that L is 50 cosine and H is 50 sine. And so therefore A is equal to 50 cosine, cosine of theta times 50 sine of theta, and that's 2500 times the cosine of theta times the sine of theta. Whatever that may be. That's the area as a function of the angle theta. Area as a function of the angle theta. If you know the angle theta, you get an area, a cross-sectional area. And now we're being asked to use Desmos to not only graph the function, but then to find the dimensions of the beam with the largest cross-sectional area. Okay, that's not too terrible. Let's go ahead and do it. And here we are over in Desmos. Now, a couple things I need to point out here is that when you normally graph using a graphing calculator, your angles that you're plugging in, these t's here, I use t's instead of theta, so it's totally fine. You could type in theta, by the way. You totally can. So I could type theta, right? And then I can change these to thetas. Theta and theta. It's the same picture, right? So, but when you graph normally using a graphing calculator, it's in radians that you're going to be looking at. Nobody graphs in trigonometry. Nobody graphs degrees versus output, because then your x-axis is massive. It goes from 0 to 360 to 720. It's massive, massive, massive. So generally speaking, we graph in radians. Well, that being said, if you think about the angle theta that we were dealing with, the maximum, actually it'll never even become this, but it has to be between 0 and 90 degrees, 0 degrees and 90 degrees, or 0 and pi over 2 radians. So I'm going to adjust this x-axis to go between 0 and pi over 2 radians. That is the maximum that I will allow for angles. The other thing you need to note here is that this is 2500 times the sine times the cosine. So we know that this area, because cosine and sine become at max 1, we know that our y values could become at maximum 2500 times 1. So we should probably adjust our y values accordingly. So our y-axis will go from a height of 0 to a height of, let's go to 3000. And now you can really see there is an actual maximum to this curve. Let me zoom out a little bit so you can see this. There is a maximum to this curve. And this is what's interesting. So I'm just giving you a kind of a level of understanding as to how people get caught cheating on exams. When people cheat on exams for graphing, it's totally obvious because they graph these vertical lines, and it's because they don't know how to scale their pictures. So in this case, you could easily see this picture scaled appropriately versus what we started with, which was this. They're totally different pictures. And so this is a very obvious somebody went to Desmos and just copied a graph versus somebody who knew what they were doing and took into account, oh, theta's between 0 and pi over 2. And let's see, 0 and pi over 2. And that the y values are going to go all the way up to 2500. So I'll just go to 3000 there. Now that's the graph of it. And we were asked to maximize. What angle would maximize this? Well, you can see we get a maximum. Remember, the outputs of the areas. We get a maximum area of 1250 when the inputted angle is pi over 4 radians. That is a 45 degree angle for theta. That is, we have a maximum area, cross-sectional area for that beam if it's a square cross-sectional area. And that's what I'm just pointing out here. We maximize this. Let me say maxed, or maybe not that actually. Area is maximized when the angle is pi over 4 radians or 45 degrees. And if that's the case, then the other angle on this side is 45 degrees as well. And you would have these, a square cross-sectional area. All right, that finishes it up for this video. I'll see you in the next one.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles. Obstacles getting in our way cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.